Welcome back again to Physics 142. In this video, I want to think about more complicated circuits where we can't just necessarily reduce the circuit into just using series and parallel combinations of resistors, try to calculate equivalent resistance just because everything is clearly in series or in parallel. And just to give an example of what I mean by that, all right, one sort of situation you could get into is what if you have multiple power supplies or multiple batteries in your circuit? Then it's a little bit tricky. Calculating equivalent resistance between sort of two resistors doesn't really make sense anymore, all right? Or you could also imagine cases, this is something called a bridge circuit, all right, where here we have 5 resistors and they're sort of all in parallel with each other and they're like in parallel and in series with each other in some sort of weird combination. And so again, this one, it would be sort of difficult to analyze this circuit to figure out how much current you have flowing through each resistor or, what the equivalent resistance is. Just using the machinery that we have so far. So to handle more complicated circuits like this, I want to introduce a sort of a set of rules or a procedure for doing that. These rules are generally referred to as Kirchoff's rules, Kirchoff's circuit rules, and they center around two concepts, concepts of loops and junctions. All right, so let's define loops and junctions and see if those are how those can be useful to us. All right, so the idea of a junction, all right, a junction in a circuit is any point in a circuit where 3 or more conductors come together. In other words, where 3 wires or more meet. All right, so a junction is where 3 or more conductors or wires meet. All right, and so example junctions here, like this would be a junction, right? We have 1, 2, 3 wires coming into this spot right here, or here's a junction with 3 wires. Right here, not a junction, right? It's just a bend, right? But here and here are both junctions, or here's a junction because there's 3 wires coming together, etc. All right, so those are junctions. And then the idea of a loop, all right? A loop is any closed conducting path. Any closed conducting path. And so here, as long as you get back to where you started, all right, you have a loop. So from here to here to here to here, that's a loop. Or all the way around here, that would be a loop, right? This would be a loop. Or you could go, all the way around, that would be a loop, or here's another loop, all right? So all kinds of loops, as long as you get back to where you started, that's a loop, okay? So Kirchoff's rules, basically there are 2 of them, all right? There's Kirchoff's junction rule and his loop rule, all right? And his rule for junctions is this, that basically if you add up all the currents going into and out of some junction, all right, you should get 0. Okay, so if you add up all of the currents going into and out of a junction, add up all of the currents going into and out of a junction, you get 0. All right? And so that's, or maybe another way of saying it is that current N equals current out. All right, so current N equals current out. All right, so current in is current out. That's the junction rule. So, let's say there was current flowing in here and out from here and here, right? This current would have to get divided into current going here and current going here. And so that sort of makes some intuitive sense to us, I hope, right? All right, so his loop rule, though, all right, the loop rule says that if you add up all of the potential differences around a closed loop, all right, so you add up all of the potential differences. Here we go up some amount potential V, right? And then here, presumably, we lose some potential, and maybe we lose more potential. We get back to where we started. So if you add up all of those potential changes, gaining positive potential and then losing potential, if you add up all those potentials, then you get 0, all right? So adding up all the potentials on a closed loop you get 0, all right? Or basically, you have to get back to the potential where you started, all right? So that's Kirchoff's loop rule. It says when you add up all those potentials in any loop, you have to get 0. So these two rules are actually really useful in determining things like how much current is flowing in each part of these circuits, all right? So as an example, I'll think about this circuit right here to start, all right? And I want to sort of step you through a procedure for understanding how we might do this. So let's suppose in this circuit, we wanted to know how much current do we get in each part of the circuit, all right? And so in each part of the circuit. All right, and so I'm going to need to understand that a little bit. We need to sort of think about what's going to happen, all right? So if we imagine some current in sort of maybe this part of the circuit, all right, well, it's going to be different from the current flowing here and the current flowing here, right? Because these this junction sort of separates these parts of the circuit. So you could imagine right here you have some current flowing, all right? And I'm actually going to label it I3 because this is also the current that would be flowing through resistor 3, right? That would be, this is all the same amount of current here, all right? Whereas then it splits, right? And you might get a different amount of current flowing here, right? A different amount of current flowing here. So I'll call that I1 because that will be the amount of current going through resistor 1, right? But then here, after this split, over here we might get a different amount of current yet, and I'll choose that current, maybe that current, we don't actually know what direction it flows, but let's say this battery pushes the current in this direction, all right? So all of this current in this region right here, that's going to be I2, all right? And so we have sort of 3 different parts, all right, that all are going to have potentially different amounts of current flowing through them. So the general procedure here, if you're faced with a problem like this, the first step is to draw in the currents in each branch of the circuit. All right, each part of the circuit that's separated by one of these junctions, right, you want to draw in the current. Now, you might not know the direction. The direction might not be obvious. In the case where you have multiple power supplies, it might not be clear. Sometimes one power supply could be way more powerful and actually drive current backwards through another power supply, all right? And so you just need to choose a direction, all right? So you pick a direction, all right? Pick a direction. And label them clearly. All right. If in the end you get that the current is negative, all right, if you get a negative sign as your answer, that just means that you chose your direction backwards, and the negative sign means that that current's actually flowing the opposite direction. All right. So don't worry too much about your choice of direction. You'll just get a negative sign at the end if you get your direction choice wrong. All right. The next step, the next thing that I do to sort of make things really help myself, all right, is I find it helpful to label the high and low potential ends of resistors, all right? So I'll explain this today. So label high and low potential ends of resistors. All right, and so how do you do that? Well, the key is that current always flows from high potential to low potential. All right, so we should note that current always flows from high V to low V. All right. And so what we can do is, if we've chosen a current direction, then we should label, all right, that this is sort of must be the positive end, and this would be the negative end because the current's flowing downhill, right? Here we would say, well, this is the positive end and this is the negative end because that's the direction we chose our current to flow, right? And here it always flows, right, from positive to negative, all right? The current's always flowing from positive to negative here, all right? And so now that we've labeled our diagram, all right, now we can use Kirchoff's laws to actually start generating some equations. So to see how this works, all right, so we need to write down Kirchoff's rules for, and you always do it for one junction and as many loops as needed. There are sometimes cases where you might use multiple junctions, but for usually multiple junctions will give sort of redundant information. All right. So let's write this down here and see what happens. So let's think about this junction right here and what this says. All right. So his junction rule says that current in equals current out. So at this junction here, it looks like I have I2 going in, I3 going in, and I1 coming out. So I would write I2 plus I3 equals I1, right? That's the relationship from this junction here. And you might notice that this junction, if I chose the other junction instead, I would get I1 equals I3 plus I2, right? So that doesn't give me any new information. So it's not, that's why I'm not going to write down another equation for this junction, because I just end up getting the exact same equation. All right? Okay. Well, this has three unknowns, I2, I3, and I1. I don't know any of them, right? So I'm going to need more equations to actually solve this problem. And so to do that, all right, it's helpful to draw some loops. So let's think about, it doesn't actually matter what loop you choose, but here let me use a different color marker to indicate a loop here. So one loop I might think about is maybe I want to draw a loop where, you know, maybe I'll start here, right? And then I'll go all the way around and I'll end back here, all right? Maybe that will be a loop that I'm interested in, all right? And so if I do that loop, what I need to do is I need to add up the potentials around that whole loop, because we know the potentials have to add up to 0, all right? So let's think about how that works. So here, when I go across this power supply, I gain a potential epsilon 1, right? So I gain a potential epsilon 1. Remember, that's the symbol for EMF, right? This sort of curly E, right, is for EMF. And EMF and potential are the same for ideal circuits, right? So that's the amount of potential that I gain here, all right? Now I go across this resistor and see here I'm going from positive to negative, so that means I'm going downhill. All right, so as long as you're flowing downhill, that means that I'm going to lose potential. Right, I go from positive to negative, I lose potential. And how much potential will I lose? Well, V equals IR. I'll lose I1 times R1's worth of potential. All right, and then here, again, I'm flowing downhill. All right, so I lose potential. So I'll also lose I3 times R3's worth of potential. All right, and then I'm back to where I started. And so the loop rule says that this whole thing has to add up to 0. All right, well, now I have two equations, still three unknowns, I2, I3, and I1. All right, this has I1 and I3. I was given, remember my givens were R1, R2, R3, and the two epsilons, right? So these were all my givens, right? And so I'm trying to find the currents. So I need one more equation, right? You need the number of equations equal to your unknowns. So I'll do one more loop, all right? I'll start here, and I'll go around, all right? Here's a loop, and I'll come back to where I started, and I'll do this sort of loop. All right, so let's say this is the loop that I do, all right? So here, all right, now I see, well, here I gain an amount of potential, right? I go, and I gain potential going across this power supply, right? So I gain epsilon 2, all right? Now here I'm going from positive to negative, So that means that across a resistor, when you go from positive to negative, you lose potential. And how much will I lose? Well, I'll lose I2 times R2. All right. And then here, I'm going from positive to negative. So again, I lose potential, and I would lose I1 times R1 worth of potential. And then I get back to where I started, that's 0. All right. Note that if I went backwards across any of these things, right, if I did this loop the other direction, I would get a negative sign, because I'd go downhill across the power supply, all right, and then I'd be going uphill with the resistors if I went backwards around, so that would change all of the signs going the other way around, all right. It doesn't really matter because it all equals 0. You just have to be consistent, all right, thinking about, well, what way am I flowing through my power supply or through my resistor? All right, so now you have 3 equations with 3 unknowns, and so that's something that you can solve, all right? I'll talk about sort of algebraic tricks for solving complicated systems in another video, all right? Here you could maybe, solve this equation for I3, solve this equation for I2, plug them both in here, then you'd only have I1s left, and you could solve that and get I1, all right? It would be a little bit nasty, but you could do it. We'll talk more about the algebra of these things in another video, but hopefully this gives you some sense for Kirchoff's rules and how they can be useful for generating equations that lets us solve these more complicated circuits.